side. We talked about cold atoms to quantum simulate models studying landscape theory.
Okay, thank you very much. Yeah, I'm Jin Zhang from University of California, Riverside. I'm a PhD student. So first, I'd like to thank this institute to offer me this great opportunity. Now I'm gonna talk about the quantum simulation using cold atoms. So first, let's to introduce our collaborators. So the Alexei Bazarov, which is now assistant professor in Michigan State University, and Yannick Muras is a professor at University of Iowa. Philip Price is from Heidelberg University, and Xianwen Tsai, she is my advisor. She gave a talk on Wednesday. I think you know her. And Judah Amos-Yaki, which is now a postdoc at Syracuse University, and Liping Yang from Chongqing University in China. So the main question is, can we build both-Hubbard quantum simulator for the Avena Hex model with a chemical potential? So we will first introduce the reformulation of the lattice Avena Hex model, which is scalar QED in 1 plus 1D using the Tensor renormalization group method. And next, we are going to consider a special limit, which is O2 model with a chemical potential, which has a superfluid phase. So here we expect a conformal field theory with a central charge C equals 1. So we propose to measure this central charge using current experimentally accessible Boas-Hubbard chains, using single species Boas-Hubbard model. But so generally, we can use two species Boas-Hubbard to simulate this model. So we so the gauge invariant classical Lagrangian formulation will be smoothly connected with the quantum Hamiltonian method in condensed matter. So next, let me introduce the Avena Hex model on the 1 plus 1D lattice. So in this model, we have a complex scalar field and attached to the sides here, and an abelian gauge field attached to the link here. So on this lattice, the vertical line is the imaginary time direction, horizontal line is the space direction. So the Avena Hex model has 3 parts. So this is partition function of this action. Now the gauge part, the first one, the gauge part is the coupling times this term. So the U x mu nu term is just a product of 4 terms around a small plaquette. So it's this term times this term times this term and times this term. So here. So why it is like this? Because we should make this consistent with continuous field theory. So in the continuous field theory, this is just the energy density of the electromagnetic field. And next is the hoping part. It's it's the linked site, link and site interaction. This is the tau direction, the vertical direction, and this is horizontal or space direction. So in the continuous field theory, it is this. And the last one is a self-interaction term. So we will only consider this situation where lambda equals infinity, where the amplitude of the matter field is frozen to 1. So the Abelian Higgs model becomes only the compact angular variable exists. This is very nice because we can use these Fourier expansions. So now the partition function can be expressed in terms of discrete sums of these modified Bessel functions. And the integral gives these two relations. So this is, we are happy about this because these n's and m's, we have physical meaning on them. So because if you see the second one, it's here. So nx tau equals m right minus m left. So it's just Gauss's law. So if nx tau is an electric charge and m right is an electric field, then this is a Gauss law. And the first one, m below minus m above. So this is the time derivative of the electric field is the electric current. Okay, so we'll use these definitions. So we divide every Bessel function by the zeroth order modified Bessel function, because this has a nice property for very large z. But this is so that the main point is we want to study this using tensor renormalization group. So we need to define some tensors on the lattice. So this is a tensor on the plaquette, and this is a tensor on the horizontal line, and a tau is a tensor on the vertical line. Okay, so let me see the picture. It's more clear. So here, this tensor B on the plaquette, in the center of the plaquette, is just this, and here, the a tau on the vertical line is this tensor. No, is this tensor, yeah. And AS tensor on the horizontal line is this tensor. Now, the partition function can be expressed by the trace of this, a product of these tensors. Now it's easy to do tensor renormalization group calculation for this. Now, first we want to find the transfer matrix T. So we consider a single time slice. We group all the tensors on this line, B, A tau B, as the capital B tensor here, and group all the tensors on this line as A tensor, capital A tensor. So the transfer matrix is square root of B times A times square root of B. Yeah, and the particle partition function can be expressed by the trace of T to the n tau. N tau is the number of sites on the tau direction. Now we are because we are going to find the Hamiltonian formulation, so we want to do the time continuum limit of this model. So in the limit kappa tau much larger than 1 and kappa plaquette much larger than 1, we keep the leading order of the eigenvalues of the transfer matrix. We get these terms. All these are expressed in amps, the electric field, and and we consider this case kappa tau much larger than beta plaquette because we want this term to dominate the energy scale. Then we can do a small spin truncation, for example, spin 1, something like that. So we define a new parameters, and yeah, and similarly we we find the leading operator leading terms for kappa s. Finally, we get to the Hamiltonian. So here the m's are the LZ, the Z component of the angular momentum, and here we have Lx. So it's spin chain with transverse field, transverse field, something like that. So here we derive this Hamiltonian formulation in under this condition, kappa tau much larger than beta p plaquette, much larger than 1. So here it seems, but if we increase the truncation of the spin truncation, this condition will be suppressed. And see if we keep many spins. So in the following, we were talking about we only keep m equals 1, 0, minus 1, the 3 state. But if we keep more, for example, 2, 1, 0, minus 1, minus 2, this condition, we don't have to. This condition will be suppressed. So this method has some applications. The first one is to calculate the Polyakov loop. The Polyakov loop is an order parameter of the confinement and deconfinement. It's a special Wilson line wrapping around the Euclidean time direction. So actually, it's just the expectation value of a product of use on a single vertical line, the world line. So using our method, we can also express this expectation value as Hamiltonian formulation. So we have an open question here. We still don't know how to measure this term experimentally because for example, for a small system, Bose-Hubbard model, can we measure the free energy of the Hamiltonian? We still don't know. That's the thing. Now, now other applications, yeah, you don't need to care about the details. So the point is, using our method, we can express many. So in most situations, we can apply our method to those models and get this Hamiltonian formulation. So it's not important. Now next we move on to a special limit. So now the beta plaquette also equals infinity, and the lambda equals infinity. Now we have the O2 model with the chemical potential here. If yeah, we still want to find the Hamiltonian formulation, so the time continuum limit is kappa tau much larger than 1, and we still can find if kappa s equals 0, we still can find the leading terms of the eigenvalues of the transfer matrix. Here we have n squared term and n term. So similarly, for the leading term for kappa s, we find it's like this. It's like the hoping term in the spin chain. So finally, we find the Hamiltonian for O2 model is like this. Yeah, this procedure is consistent with the method by Fradkin, Susskind, Kogut, Polyakov. So they can directly do time continuum limit, like if you decrease the lattice spacing in tau direction and do some calculation, you still can get this Hamiltonian. Now for U tilde much larger than J tilde, because this term will dominate the energy scale, we use spin 1 approximation. Now and then furthermore, if the chemical potential mu tilde is tuned to U tilde over 2. So then the O2 model is approximately by a single species Bose-Hubbard model, like this. And here, this J equals J tilde over 2. We want to know how good is this approximation. So we calculate the second order Renyi entropy for O2 model and this single species Bose-Hubbard model for 16 sites, open boundary condition. Now for O2 model is the colored stripes here. As we increase the chemical potential, it starts from the zero particle density. This is a multi-insulator from 1 particle and 2 particles, 3 particles. And here it's a multi-insulator with unity filling. And the black lines is for Bose-Hubbard model. We see that if J over U is really very small, these two models are nearly the same. So we will working on this region. Now we will calculate the entanglement entropy. First, let's introduce the nth order Renyi entropy. It's like this. So the limit n goes to 1 is the von Neumann entanglement entropy. Calabar, Sprace, and Cuddy predicts that the nth order Rayleigh entropy behaves like this. It scales linearly with the logarithm of the lattice volume. And here C is the central charge. For O2 model, the central charge C equals 1. Now, because this is a leading order that requires a very big lattice, but experimentally we can only reach small volume. So we need to consider all the corrections, including all finite size corrections we have known. We find we will fit this Rayleigh entropy data by this function. So we add oscillation term and 1 over log square term. So here this little l is the length of the subspace A. Now we are going to fit this data. So first numerically we use DMRG to calculate the second order Rayleigh entropy and the first order Rayleigh entropy, which is von Neumann Rayleigh entropy. We use this to fit this data. We can see that this function fit this data very well, and for the parameters a n here, which is related to the central charge here, is very it's consistent with a theoretical prediction. It's very close. So this is for kappa s, for kappa s, kappa tau equals 0.01. In this language, it's j tilde over u tilde equals 0.001, which is in this region. So we prove that in this region, because we will prove that in this region the two models are the same. So first we calculate the O2 model for such parameters. We calculate up to ns equals 64. The next one is for another parameter set. This is for j tilde over u tilde equals 4. So you can see for O2 model, it is still fits very well, and the parameters here also consistent with a theoretical prediction. But we want to verify this experimentally. So we need to compare the Rayleigh entropy of O2 and the Bose-Hubbard model. So here there are two graphs. This one is for j over u equals 0.005. So j tilde for j tilde over u tilde, this is 0.01. We can see that the Rayleigh entropy are nearly the same for the lattice space up to 16, lattice length up to 16, and this is for j over u equals 0.1. We can see that there is some difference, but we can say that this is not big, because because for we experimentally preparing both hybrid model for such a small J over U is impossible. At least for now, we will show. We will talk about this later. So next, we want to say how big the system in experiment we should prepare. So we plot this graph. So here n as max is the maximal lattice length we used to fit this data. So we see that if we for this graph, J over U is very small. We see that up to 64, it nearly go to the theoretical values. But we can see that this is for 12, and this is for 16. And 18, 18, 20, 10, maybe, yeah, 10, 12, 14, 16. Oh no, this is 20. Oh, sorry. Okay, okay. So, NS is the length of the sentence of the system. Bound dimension? Oh, yeah. We didn't fix the bound dimension. We keep increase the bound dimension until the truncation error is less than 10 to negative 10. Okay. For periodic boundary condition, for the longest system, the bound dimension is the order of 1,000. Yeah, but for open boundary condition, it's several hundred. It's much smaller. Okay. So here we want to find us how small we can keep this system to still have a good results. And here this is also for J over U equals 0.1. And this dark stripe is a defect. No, is so if we have 5% error, this is a 5% error region. We can say that 16, maybe more than less than 20 sites is okay for to approximate to have a good result. Now let's see the experimental proposal. Let's see the B figure. So the B figure is to diabatically prepare the ground state, half-filling ground state. So initially we have the multi-insulator. For example, this is for 4 particles in 8 sites. So multi-insulator, 4 particle, and then we plus 2 walls on the boundary, and plus harmonic confinement. And we diabatically reduce the confinement. We will finally get the ground state of ground state of the half-filling Bose-Hubbard model. So let's see the simulation. So here we use U is 1 Hertz and J is 100 Hertz. And the harmonic confinement decrease like this. We see that for 2 particles on 4 sides, it starts from here, and after several milliseconds, it will go to the ground state of this half-filling Bose-Hubbard Hamiltonian. And similarly, for 4 particles on 8 sides, it starts from 0. The time scale is also small. So after, you can see after like 40 milliseconds, we still go to the ground state. Okay, so this graph is to show how we can measure the entanglement entropy, the second order ring entropy. So we prepare 2 copies of the state. So the 2 copies are the same. Then we do beam splitter operation. Then finally we measure the particle number for one copy. So this is the theory. Now, if we can measure the number at each site in 1 copy, the second order ring entropy is just the expectation value of the parity of the subsystem where you want to measure the entanglement entropy. Now the parity, the probability of this parity is just 1 plus minus e to the negative s2 over 2. So we can find that the statistical error is like this. So we did some approximation. We did some estimation that if for example, if the in experiment we can prepare the lattice length up to 16. So the S2 is order of 0.7. Then we estimate that the classical entropy, which is the defects in the experiment, per particle is the order of 0.05. So the maximal measured S2 is less than 1.1. If we want to measure the S2 within this error 0.1, it's like it will take about 800 measurements. It's not a big number, and due to the logarithmic growth of S2, the number of measurements needs increase like ns to 1 over 4. So it's not a prohibitive growth. We can measure it. Now, finite temperature effects. So let's just first see this graph. As I said before, we chose J over U equals 0.1 and not 0.01 because for small J over U, it's very sensitive to the temperature. So you see that this is a simulation for J equals 0.05 here, 0.01 here and 0.2 here. So the temperature is 0.004. So for smaller j, the temperature effects is bigger. So so we can't prepare such a small j over u experimentally. So as a compromise, we chose j over u equals 0.1. And this. For this graph, we want to show the possible experimental outcomes because we haven't done the experiment. We just simulate the numerically. So we synthetically generate the data with random Gaussian fluctuations with sigma 0.02, and now we do we fit this data each time, and we will find the error in coefficient A2. Approximately is 3.1 times the error in S2. So yeah, actually this is for one situation. Actually we did many many cases. We did a linear fit to get this. This is not shown here. So this result shows that we can we can control the error in the experiment. The error we measure we can control the error of this the central charge by control the measure of the second ordering entropy. Okay, this is so until now we show that our methods is valid for O2 model. Actually, it will be valid for many cases. We want to. So an interesting thing is the time evolution. So this is the first step for doing the time evolution. We did sudden expansion, which is we put m particle. We put m particle on one side of the lattice and let they expand inside two n sides. So this is sudden expansion. But for here, for just for j over u is 0.01, we find that the second ordering entropy thermalize. It doesn't thermalize for such a small system like ns equals 4 and ns equals 6. There's many big fluctuations, and it seems like there is some periodic fluctuations. But start from L equals ns equals 6. It starts thermalize. Yeah, we can. This is a particle density on each side. It shows the same property. I will continue. So can we do bigger j over u? Because we know that for bigger j over u, the thermalization will be better. I mean, it will be thermalized much quicker than this. So we can use two species post-Hubbard model to simulate this model. Now this is two species both Hubbard model we use. There is a hopping term and the chemical potential term. Now here this is interspecies interaction, interspecies interaction, and the nearest interaction, nearest site interaction, and this is hopping between different species. So if we want to do spin 1 truncation, we need to keep NA plus NB equals 2, because we can't do that, because if we tune these parameters like this, this parameter is much larger than other energy scale. We find that this model will stay in the lowest energy sector. This is where NA plus NB equals 2. So these three states, 2, 0, 1, 1, 2, 0, 2, is just the spin, represent the spin model of spin 1, spin 0, and a negative 1. Then, using the second order perturbation theory, we can find the spin model. Now we have everything here: the LZ and the hopping and the LZ square. So actually, we can tune these parameters to some specific value, and we will get those model we have shown in the last before. So this is for the first one, the Abelian Hex model, not the O2 one. It's the first one and the M one. So we compare the energy spectrum. We find that the two species both Hubbard model matches the spectrum very well, and for this is the O2 model, and we also find good matches for the spectrum. So this is not good. So this is the lattice implementation. The first one is species-dependent lattice. The interspecies interaction W can be tuned by the Feshbach resonance. Because there's no time, we want to go to the details. The second one, it may be a simpler one. We use a single species, but the ladder on two sides express two species. This represent A species, and this represents B species. So the only so here, because VB equals negative y over 2, it is negative. So here there's a problem. So maybe the details we are considering, but this interaction can be realized by the dipole interaction, which is attractive. Now this is conclusion. So we propose a gauge invariant approach for the quantum simulation of Abelian Hex models, and calculations of entanglement entropy for O2 model in the superfluid phase is consistent. Consistent with the safety prediction of central charge 1, and this is the main part. The current experiments using cold atom trapped in one-dimensional optical lattices designed to measure the second-order entropy can be used to verify the detailed predictions of conformal field theory and the estimated central charge C. And finally, we proposed two species both Hubbard model to simulate the whole thing, proposed an implementation. Although there are not very details, but we are working on that. we're able to match the spectra in a large unit. Okay, that's all. Thank you.